Hey guys, so today I'm going to be going over double integrals over rectangles. So really quickly, before we get into how to evaluate it, I just kind of want to talk a little bit about what a double integral represents. So I think this will be most helpful if I draw a little picture here. So we're going to have a function, little surface fxy. So this is fxy, it's a surface here, as you can see. And basically what a double integral does, previously when you've calculated integrals, it's been area to find area under the curve. I feel like that's the phrase most associated with integrals. In double integrals, we're finding the volume. So to do that, you project this down. Basically, you're just drawing lines from each of the corners all the way down onto a surface. And in this case, the surface is going to be a rectangle, as you can probably tell by the title. So you project it down onto a rectangle. And to evaluate a double integral, you want to find the volume of this. And you do that by finding a sample volume. So you take a little piece out of this big one, this big surface up here, and you project it all the way down onto this surface here, and you get a mini little rectangle in the bigger rectangle. And this is your sample volume. And this will help us calculate the bigger volume. So this right here is the sample volume, and I just projected it down onto the XY plane. And it's important to know that we call this region D. This just is for notation purposes. Honestly, you can call it whatever you want. But now onto what this represents. So we know the volume of this. So let's try to find out what the volume of this little sample volume is going to be. So this right here is going to be a small change in y, so dy, and this right here is going to be a small change in x, dx. So the area of this is going to be dy dx. So the sample volume is going to be dy dx, which is the area of this, times the height. And in this case, the height is fxy. So we have the sample volume as fxy. Okay, and it makes sense that you can interchange dx, dy. It's not going to really change anything. But this leads us into the formal definition of double integrals over rectangular regions. Like I said, you're calculating volume here, so the volume is going to be equal to the double integral over region D. Like I said, this whole thing here is region D. So makes sense that you're going to project everything over this region D, and then you're going to multiply by a sample volume. Not multiply, you just have double integral over region D of the sample volume. So we know that the sample volume is equal to this thing right here. So we have the double integral over the region D, and just for convention, I'm going to put fxy first because, usually you have the differentials at the end, so dy dx. And you can simplify dy dx to the area, because this is the area of a sample down here. So this can be dA, which gives us double integral over the region D fxy dA. And this is the little bit more formal definition. So this actually leads us to a theorem called Fubini's theorem. And it's very important to note that Fubini's theorem only works for rectangular regions. It's not going to work if you have a triangle or a different region. So Fubini's theorem basically says that dy and dx are interchangeable. That's all it really says. And this makes sense because it doesn't matter which one you multiply by first. You're still going to get the same area of the same sample rectangle, right? So just to put that in a little bit more notation format, we have a double integral over the region D fxy dA is equal to, from a to b, c to d, and these are the bounds for x, these are the bounds for y, fxy dy dx. And you can also change up the order. So we have double integral from c to d, a to b, fxy dx dy. And notice how the bounds match the differential. We have a to b for x, a to b for x, and then c to d for y. And that's continuous throughout. Okay, so let's do a little example. Okay, so this is the example problem. We have evaluate the double integral over the region D, x squared y dA, where D is the region bounded by 0 to 3 for x and 1 to 2 for y. So when evaluating double integrals, one of the most important things is finding the bounds, because that is what the differentials matter on or depend on. So you definitely want to identify the bounds. So to do that, we need to find region D. We need to know what region D looks like. We know it's a rectangle because it's two numbers, first of all, and second of all, the title is over rectangles. So I always recommend drawing region D. It just makes it a whole lot easier, and we know region D is in the XY plane because we have X and Y. So X is between, okay, just ignore that. It's between 0 and 3, and Y is between 1 and 2. This is not to scale. So we know that X goes from 0 to 3, and Y is from 1 to 2, so we're gonna have a rectangle that looks like that, and that is region D. So you want to find the bounds, and you will not always be given bounded by. This is just a nice problem. So let's just go through as if we weren't given this, all we were given was this rectangle. Let's find the bounds for X. It's pretty easy to look at. You just see, oh, X goes from 0 to 3. And what about Y? Goes from 1 to 2. And so those are the bounds. Now we just have to set up a double integral in one of these two formats. And so because of Fubini's theorem, we know that it's interchangeable. Sometimes it'll be easier to do dy dx, sometimes it'll be easier to do dx dy. In this case, it doesn't really matter too much. So we're gonna just do both. So let's do this one first. So dy is on the inside, dx is on the outside. So first I'll set up, oh, and fxy is just the given function here. So this is the surface, I'm just putting that in there, and then we have dy dx. So like I said, you want to match up the bounds. This is very important. This is where a lot of mistakes are made. You want to make sure the bounds match. So you can see that y, dy is first, so that is the inside integral. Y goes from 1 to 2, so I put that on the inside. X is the outside differential, so therefore I'm going to put 0 to 3 on the outside integral, and this is the volume. And now let's set up the other one. X squared y dx dy, and this, x is on the inside, x goes from 0 to 3, y is on the outside, 1 to 2. Okay, then quickly evaluating these, I'm just going to go through this one up here. I'll just choose this first one up here to evaluate. So coming down over here, we have 0 to 3, 1 to 2, x squared y dy dx. Okay. I'm going to evaluate this one. So we're going to treat, because I'm integrating with respect to y first, I'm going to treat x as a constant. So x squared is just a constant here. So when I integrate, I'm treating x as a constant. So y, the integral of y is 1/2 y squared. But I'm going to have 1/2, x is a constant, x squared, y squared, from 1 to 2, dx. And this gives you 0 to 3, and these bounds I'm only going to plug into y because we were integrating with respect to y. So I'm leaving x alone the whole time. I should end up with an x squared. So we're going to have 1/2 x squared, 2 squared is 4. I'm going to put 4 up there, minus 1 over 2, so 1/2 x squared dx. And now we can integrate with respect to x. 0 to 3, I'm just going to simplify this, but this becomes 2x squared minus 1/2 x squared and dx. Okay. And then integrating with respect to x, I should get 2/3 x cubed minus 1 over 6 x cubed, 0 to 3, and that would give me, plugging this all in, 27 over 2. Okay, I hope that was helpful. Thank you so much for watching.